Okay, good afternoon, all of you. So, already this is the fourth lecture of your probability, and in the previous class, we gave you the concept about the conditional probability mainly, and on the basis of that, we have proved several important theorems, and especially Bayes theorem, and some applications of Bayes and other examples. Today, we will focus on independence of two events or maybe more than two events. So what is the stochastic independence actually? Actually the term is stochastic independence. So look at that. First I will start with a lemma. If A and B are independent events, then probability of A given B occurs is equal to probability of A. If A and B are independent, that means A and B are independent and A doesn't depend upon B. Whether B is happened or not, B has occurred or not, that do not have any effect on A. Also, for any pair of events A and B, probability of A intersection B is equal to probability of A given B occurs into probability of B equal to probability of B given A occurs into probability of A. So this thing we have learned from conditional probability. But you see, if these two are independent, A and B are independent, then from the last lemma we see that another interpretation of independence is then knowing B doesn't change the probability of A actually. B doesn't change the probability of A. Okay? Now we can define more formally the independency of two events. So if A and B be events in a probability space omega AP, this is your probability space where omega is the class of events, event space, F is the class of subsets of omega, and P is the probability function. Already we defined these things. So we are talking about this probability space, and A and B are the events in this probability space. We say that A and B are stochastically independent, or simply you can say independent. Actually the statistics terms comes from the stochastic word. If and only if probability of A intersection B equal to probability of A into probability of B. Actually you see that in the lemma, probability of A given B occurs is probability of A. So naturally this will be your, this first term, this is the first product of two probabilities. So the first probability will give you probability of A, and it comes from this definition, this lemma actually, that probability of A intersection B is probability of A into probability of B. So this is the definition of independent, most formal, and this is actually if two events are independent, then probability of A intersection B is equal to probability of A into probability of B. If it is found that probability of A intersection B is equal to probability of A into probability of B, then the events are independent. So that is why it is if and only if condition. Okay. And next there is a theorem without any proof, just a simple theorem. For any two events A and B with probability of A greater than 0 and probability of B greater than 0, the following statements are equivalent. So what is that? First one is that if two events are such that both are positive, then probability of A intersection B equal to probability of A, probability of B, that is actually related to independency. Okay, and probability of A given B occurs is equal to probability of A, and number 3, probability of B given A occurs is equal to probability of B. So that is, these statements are equivalent because this comes from the concept of independency. If two events are independent, this holds, and obviously if A and B are independent, they are not dependent on each other, then you can write probability of A given B occurs equal to probability of A, and probability of B given A occurs equal to probability of B. So these three statements are equivalent. That is why. Let us have an example of how will you solve or apply in the problems of probability, the independent. So a card, a very simple problem. A card is chosen randomly out of a deck of 52. You know that there are 52 cards in a pack. So there are spades, clubs, hearts and diamond. All are 13. So 4 13 is 52. All cards are equally likely. A is the event that the card is an S. So there are 4 S's. Okay. And B is the event that the card is a spade. So there are 13 spade. C is the event that the card is a jack of diamonds. So there is only one jack of diamond or 2 of hearts. So there are 13 hearts, diamonds also 13. D is the event that the card is an even number. Okay. So there are the D is the card of even number. So there are 20 even numbers. Okay. So let us now find out all the events are defined here. Let us now find out probability of A intersection B. What is your probability of A intersection B? That is, what is your A? First you observe A is the event that the card is an S, right? And there are 4 S's. S means this one. This is called tekka sometimes, and in your colloquial language. And B is the event that the card is a spade. So B is the event that the card is a spade. So there are 13 spade. So what is the meaning of A intersection B? That means ace of spade. If you combine these two, then that the meaning of this A and B, that means ace and spade, and that is only one possibility. So the probability of this is 1 by 52, right? 1 by 52. And you see, this is equal to, you can write, now what is the probability of A? If you want to write probability of A, what is the probability of A? Probability of A equal to 4 by 52, right? Because there are 4 S's out of 52. So 4 by 52 into, if you want to write probability of B, what is your probability of B? Probability of B is card is a spade. So there are 13 spade out of 13. So 13 C1 by 52 C1. So that is nothing but your 13 by 52. So it gives, these two are equal. These two values will be equal. So you see A and B are independent. From this experiment, this calculated result, we can say that A and B are independent. A and B are independent, right? So this is from the calculation, and you see, you can check this, verify this. And now comes let us calculate intersection probability of C intersection D. Let us now calculate probability of C intersection D. What is your probability of C intersection D? C is the event that the card is a jack of diamonds or a 2 of hearts, right? And D is the event that the card is an even number. So there is only one possibility, jack of diamonds and 2 of hearts or 2 of hearts. So this is nothing but your 1 by 52, because if it is an even number, then it must be 2. So 2 of hearts or jack of diamonds. It cannot be jack of diamonds. It must be 2 of hearts, because you are taking C intersection D, and D is the card is an even number. So 1 by 52. But you see, if you calculate probability of C into probability of D, right? What is your probability of C? What is your probability of C now? Probability of C is jack of diamonds or a 2 of hearts. So that is 2 by 52, right? And D is the card is an even number. So card is an even number means 20 possible cases. So favorable cases by classical definition you are applying. So 20 by 52. So 20 by 52 and 2. So this is not equal to this. That means from this calculation and the results, we verify that C and D are not independent. So C and D are not independent, right? So this is the application, how will you apply in the simple problems of probability the independency, independent, or whether the two events are not independent. Okay, so let's come to the next part. Mutual, we will talk about mutual and pairwise independence of more than two events. We shall now talk about mutual, what is mutual independence, what is pairwise independence. So three events, first we'll define for three events ABC are said to be pairwise independent if probability of A intersection B equal to probability of A into probability of B, and probability of B intersection C equal to probability of B into probability of C. Probability of C intersection A equal to probability of C, probability of A. These are the conditions for pairwise independent. Okay, this is called pairwise independent. And what is mutual independent? Mutual independence means these three relations will hold, these three will be there, and with this addition you have an additional condition that probability of A intersection B intersection C equal to probability of A, probability of B, probability into probability of C. This is called mutual independent. So look at that. For pairwise independent you have three conditions, and for mutual independent you have an additional condition. This is the additional condition, the last one, that is the intersection of three events equal to the product of their probabilities. Intersection of probability of their intersection is equal to the product of their probabilities. So now we can generalize the concept. We can generalize the concept for pairwise independence. Let us define for n events A1, A2, An, then the pairwise independent if probability of AI intersection AJ is probability of AI into probability of AJ. For I not equal to J, Ij equal to 1, 2, 3, n. So this is called pairwise independent for n possible events, n events. So you can generalize the thing. Also for mutual independence, similarly you can define this one. It's mutually independent if for any subfamily B1, B2, Bj of A1, A2, An, this relations hold, this additional relation hold. Okay, this is for mutual independent and pairwise independence. Now let us have some important observations on that. First one is that, first there is a question for all of you. How many ways can you define mutual independence of n events? How many ways you can you define mutual independence of n events? That means how many relations you need for n greater than 2. For n greater than 2. So it can be NC2, right? It can be NC3 or NC4 or etc. NCN. And that is equal to 2 to the power n minus n minus 1, right? So this is the result. Actually sum of the binomial coefficients is equal to 2 to the power n, and you are transposing NC0 NCN to that side, so it will give you this result. Sorry, my screen is, yeah, I got my screen. Yeah, now this is okay. So this is the simple question to all of you, and this is the answer. You can verify the answer. Next I will talk about another important observation. Mutual independence implies pairwise independence. Okay, but the converse is not true. You look at that, what is the concept of mutual independence? This is pairwise independence, and mutual independence there is an additional condition. So the note observation is that mutual independence implies pairwise independence, but the converse is not true. So let us have an example. With that example I will explain that thing. So let E be the random experiment. of tossing two coins or a coin two times in succession, right? So it's a tossing a coin, two times in succession, right? Okay, so this is the experiment, and the event space is given by, so your space will be, event space will be head head, head tail, tail head, and tail tail, right? This is your event space. Now where H denotes the head and T denotes the tail. Now let ABC be the event. Let A be the event. What is A? Let us define head appears in the first toss. Okay, and let B be the event. Let B be the event. What is B? B be the event. Head appears in the second toss. So let us copy these things. It will be more faster. Head appears in the second toss, right? And let C be the event. What is C? Head appears only one head. Only one head. Okay. So these are the events. Let us define A as the head appears in the first toss, B heads appears in the second toss, and C is the event that only one head. So what is your A? A will be head head and head tail, right? What is your B? B will be, what is your B? B will be head appears in the second toss, so you can take head head and tail head, right? And C is the event only one head, so C equal to, we can say head tail and tail head, because it's talking about only one head, right? So this is the, so what is your B intersection C? What is your B intersection C? That is your tail head, right? What is your C intersection A? What is your C intersection A? Head tail, right? What is your A intersection B? What is your A intersection B? That is your head head, right? Okay. So, and what is your A intersection B intersection C? You look at that, that is phi. That is null set, right? You go through the example, you will get A intersection B intersection C equal to null set. So by classical rule, let us now calculate probability of A. What is your probability of A? 2 by 4. Okay. And what is your probability of B? 2 by 4. And what is your probability of C? 2 by 4, right? So all the events you will get 2 by 4. Okay. And what is your probability of A intersection B? A intersection B equal to 1 by 4. Okay. And that is equal to probability of B intersection C and C intersection A. So B intersection C equal to probability of C intersection A equal to, they are also 1 by 4, right? They are also 1 by 4. And what is your probability of A intersection B intersection C? That is equal to 0, because that is a null set. That is a null set. So this is 0. Okay. So this is equal to 0. So now you can come and verify that probability of A intersection B equal to probability of A into probability of B. That you can verify here, because probability of A is half, probability of B is half, and their product will be 1/4, and probability of A intersection B is 1/4. Also probability of B intersection C is equal to that. So you can write that probability of B intersection C equal to probability of B into probability of C. So that is true for these two events also, B and C, and that is true for C and A. Got it? Okay, that makes sense. So what is your conclusion now? They are pairwise independent. What is your conclusion now? In this case, your conclusion is that the events are pairwise independent, right? So this is your conclusion at the final stage. Now for A intersection B intersection C, what is your conclusion? You see, probability of A into probability of B into probability of C, that will be 1/8. So if you multiply, so if you write probability of A intersection B intersection C, that is equal to 0, and that is not equal to probability of A into probability of B into probability of C, because the product will be half into half into half, that is equal to 1/8. So that is not equal to. So what is your final conclusion? They are not mutually independent. A, B, C are not mutually independent, but they are pairwise independent. So what was my observation in this thing? Mutual independence implies pairwise independence, but the converse is not true. That is, pairwise independence do not implies mutual independence, but mutual independence implies pairwise independence. So that is the very important conclusion, and the converse is not true. So you can verify this with an example, right? Next observation. Next is that it is to be noted that concept of mutually exclusive events and independent events are not equivalent. Okay, we'll give you two examples to actually verify the result. So example 1 is that, suppose okay, let me write in this. In the example 1 will show two events may be mutually exclusive, but and not independent, okay. First we'll show that two events may be mutually exclusive. People are thinking about that maybe mutually exclusive events and independent events are equivalent, but not so. I will give you two examples for that. First I will show that two events may be mutually exclusive and not independent. So let us again the same example. I will start with the same, tossing a coin 2 times in succession. So you have a event space head tail head. So let us give you that example. So the example give the event space head tail head and tail, right? So where H is denotes the head and T denotes the tail, where A and B, what is your A event now? Let me define A event in suppose both the coin show head, show head. And what is your B? B is the event both the coins show tail, right? Both the coins show tail. Okay, both the coins show tail, right? So these are the two events. So what is probability of A now? Because if both the coins show head, that means this is HH, and if both the coins show tail, this is tail, right? These are the possibilities. So what is, you see, A intersection B is phi. They are mutually exclusive. Okay, got my point? A and B are mutually exclusive. Now what is your probability of A? 1/4. And what is your probability of B? That is also 1/4, right? Okay, and you see that what is your probability of A intersection B? 0, because A intersection B is phi, mutually exclusive, and that is not equal to probability of A into probability of B. Okay, okay, so what is your conclusion? A and B are not independent. A and B are not independent. We are not independent, right? So A and B are not independent, but they are mutually exclusive. So that was my target actually. That is my target, and we have proved that with an example. We have verified that the two events may be mutually exclusive and not independent. Okay, next we'll show next example. Next example will show that two events may be independent, and not mutually exclusive, right? Not mutually exclusive. Two events may be independent and not mutually exclusive. That we have to show. Let us consider the tossing of, let us consider, for example, let us consider the tossing of two dice together. Tossing of two dice, or you can say throwing our two dice together. Okay, tossing or throwing, you can say, that word can be used. Throwing of two dice together. Okay, experiment. So the event space consists of 36 event points, right? So 6 square equal to 36 event points, because you are throwing two dice. Let A and B, let A be the event. What is A? A be the event that the face 6 appears in the first toss. Okay, in the first die, sorry, in the first die. And let B be the event. And what is your B? B be the event that face 6 appears in the second die. Okay, let's copy this one. Face 6 appear in the second die. Okay, this is A, this is B. Face 6 appear in the first die and face 6 appear in the second die. So you look at that. What is your, actually A and B contain 6 event points, and what is your A intersection B? What is your A intersection B? Contains only 1 point. Contains only 1 point. So A and B are not mutually exclusive, right? 6 appear in the first die, and that contains actually the point 6, 6, right? Okay, so what is your probability of A now? Calculate. What is your probability of A? That is 6/36, right? And what is your probability of B? 6 appear in the second die, so that will be also 6/36. So 1/6 and 1/6. Now, what is your probability of A intersection B? What is your probability of intersection B? Look at that. If you combine these two, 6 appears in the first die and 6 appears in the second die. So that constitutes only one point. Only one case, 6, 6. So 1 by 36, right? And that is equal to 1 by 6 into 1 by 6. That is equal to nothing but your probability of A into probability of B. Okay? So what is your conclusion now? What is your conclusion now? That A and B are independent. A and B are independent, but A and B are not mutually exclusive, because A intersection B is not equal to phi, right? So let me write the conclusion at last, that A and B are independent, but they are not mutually exclusive. Okay, so that these are the very important observations while you are doing some problems on that. The two events may be independent but not mutually exclusive, and two events may be mutually exclusive and not independent. So mutually exclusive and independent are not equivalent. That have to be justified with examples. So these are the examples and these are the conclusions. Okay, now so maybe there is a question in your mind that two events A and B can be both mutually exclusive and independent. When it is possible? Only when at least one of the two events have a zero probability. At least one of the two events A and B has zero probability. In that case, probability of A intersection B equal to probability of, in that case your probability of A intersection B equal to probability of A into probability of B equal to 0. Okay, in that case only it is possible. In that case it is possible. One of the events should be zero probability. In that case only it is possible that two events are independent and mutually exclusive. Otherwise, for non-zero probabilities, it is not equivalent. Clear? So these are the cases. Next, let us solve some important worked out examples. Let us have some important examples. First one is that find the probability of occurrence of exactly one of the events A and B. What is the probability of occurrence of exactly one of the events A and B? So let us draw a Venn diagram first. This is your omega and this is your A set, and okay, let me draw little bit larger A, and this is your B. Okay, so this is your A and this is your B, and this is your A intersection B complement, and this region is A intersection B, right? And this part is your, what is this part? A complement intersection B. Clear? So these are the region. So what you can say, A intersection B and A intersection B complement are mutually exclusive. So you can write from this diagram, from the, okay, or from probability you can write axioms of probability. You can write using axioms of probability, probability of A equal to probability of A intersection B plus probability of A intersection B complement. Okay, okay. So now you look at the diagram also, and from here you can write probability of A intersection B complement is nothing but your probability of A minus probability of A intersection B. Okay, and similarly you can write Similarly, you can write this one. Similarly, you can write with the similar conclusion. What you can write? Probability of A complement intersection B equal to probability of B minus probability of A intersection B. Okay? These are the two relations. Now, what do you want? Probability of occurrence of exactly one of the events A and B. Probability of occurrence of exactly one of the events A and B. So, the required probability is equal to probability of A complement intersection B union A intersection B complement. Okay, you look at that, exactly one of the events A and B. So that implies this union this, either this part or this part. So in the first case, you that occurrence of B or occurrence of A. There is a sense of or. So which implies, since A complement intersection B and A intersection B complement are mutually exclusive, so we can write probability of A complement intersection B plus probability of A intersection B complement. And you got the result 1 here, result 2 here for probability of A intersection B complement and probability of A complement intersection B. You substitute these two results, so that will give you probability of A minus probability of A intersection B plus probability of B. Okay, this should be A. In the first case, this should be B. Actually, I have written A complement intersection B first. So this is B. This is A minus probability of A intersection B. Using relation 1 and 2. Using relations 1 and 2. Got it? Now what is the final result? Final result will be probability of A plus probability of B minus twice probability of A intersection B. This is the result. Clear? Okay. So what is your requirement? Occurrence of exactly one of the events A and B, and this is the result. This is the result of occurrence of exactly one of the events A and B. You can use this result in problems also, and maybe somewhere the question is that you have to find out this is the process how to find out the result. Next example is find the probability of occurrence of at least one of the events A and B. In the previous case, you have exactly one of the events A and B. Now you have at least one of the events A and B, and that you know that can be used using these two results. Using these two results, you can say that is given by, I am not doing the whole process. This is required in the next proof. These two relations 1 and 2 are required over there. So your required probability will be, actually I want at least one of the events. I want at least one of the events A and B. So that implies, so I'm writing the required probability here directly. I'm using the previous knowledge. Required probability equal to, what is that? That is nothing but your probability of A union B. Actually, union concept is that is the concept of at least one of the events, right? So at least one of the events A and B means the union of A union B. So look at that, union consists of A intersection B complement, A intersection B, and A complement intersection B. Okay? Okay? this constitute the union. So we can write replacing union by probability of A intersection B union A complement intersection B union A intersection B complement, right? So this is from the, you observe this is by this one, okay? So we can write this union and this. Now these are mutually exclusive. Now these events are mutually exclusive. A intersection B, A complement intersection B, A complement A intersection B complement, these are mutually exclusive events. So we can write probability of A intersection B plus probability of A complement intersection B plus probability of A intersection B complement, okay? And using relations 1 and 2 in the previous result, 1 and 2, let us use 1 and 2 in this case. So what is that? Probability of A intersection B and probability of B minus probability of A intersection B plus probability of A minus probability of A intersection B using relations 1 and 2, and you will get finally, what is the final result? The addition rule, theorem of total probability for two events. Actually this is nothing but your theorem of total probability for two events, okay? Okay, this is the result. So this is nothing but your at least one of the events A and B. This is the sense. So this is another approach of doing that. Next, okay, show that two events A and B, example 3 I am talking about, show that the events A and B are independent if and only if, there is a if and only if conditions, A and B complement are independent, okay? So you see, again, if we look into the diagram, if we draw the diagram once again, or you can see the diagram, A can be written as, what you can write from A, for A is the union of these two mutually exclusive events, A intersection B complement and A intersection B. So once again I repeat, A is the union of these two mutually exclusive events, A intersection B complement and A intersection B. So we can write, let me write A, probability of A equal to probability of A equal to probability of, or suppose you write simply A can be written as, okay, probability of A intersection B union A intersection B complement, right? This can be written as. Now these two are mutually exclusive, A intersection B and intersection A intersection B complement. So what we can write? We can write that A intersection B plus probability of A intersection B complement, and that makes sense, right? Okay, because these two events are mutually exclusive. Now this is relation, suppose 3, because already I gave 1 and 2 as the relations. So let us now suppose that A and B are independent. Let A and B are independent, right? So if A and B are independent, what is the meaning of that? You can write probability of A intersection B equal to probability of A into probability of B, okay? So from 3 you can write, probability of A equal to probability of A into probability of B plus probability of A intersection B complement. Okay, now you transpose, if you take it, transpose this quantity to the left hand side, then you can write A intersection and do some manipulations on that. So you can write A intersection B complement equal to, you can take probability of A common. After taking common, you can write 1 minus probability of B. Okay, so 1 minus probability of B is nothing but your, what is that, complementary event, right? So that is equal to B complement, probability of B complement. Okay, and this proves that probability of A intersection B complement is probability of A into probability of B complement. So this proves that A and B complement are independent. So you have started from A and B are independent. From that you prove that A and B complement are independent. So what is your conclusion here? A and B dashed, that is the complement, are independent. Now you assume that, secondly, next let that A dashed and B dashed are independent. Okay, A and B complement are independent. We have to prove A and B are independent. So again you have to write that equation, probability of A equal to probability of A intersection B plus probability of A, this one I am writing this relation. Now A and B complement are independent, so we can write probability of A into probability of B complement, right? Okay, since A and B complement are independent, again transposing this quantity to the left hand side and some manipulation, you will have probability of A intersection B equal to probability of A into 1 minus probability of B complement, right? And what is your 1 minus probability of B complement is nothing but your probability of B. So that is equal to probability of B. So you prove that, finally this proves that A and B are independent. A and B, that is the events A and B are independent. Okay, so this is the if and only if condition. First you have assumed that A and B are independent. With that assumption you prove that A and B complement are independent. Next you assume that A and B dashed are independent, that is the independent. From that you have proved that A and B are independent. Okay, also in the last section I will show you one more thing, that is if A and B are independent, let me show you last part. If A and, it's an event A and B are independent, then A complement and B complement are also independent. So if A and B are independent, we can also prove that, this is also example, A complement and B complement are also independent. So let us start. So A dashed intersection B dashed, right? We have to start this. Now we can apply De Morgan's law here. So we can write probability of A union B whole complement, and that is nothing but your 1 minus probability of A intersection B, A union B, right? Because probability of complementary event is equal to 1 minus probability of that event. So that is equal to, and you can put your general addition rule here. So probability of A plus probability of B minus probability of A intersection B. Okay, expand. If you expand this, open the bracket, you will get 1 minus probability of A plus minus probability of B minus plus, and A intersection B is probability of A into probability of B, because A and B are independent. So you can write probability of A into probability of B because of their independency. Now you can take 1 minus probability of A, you can take a common, you can take a pair of them. So minus probability of B, 1 minus probability of A. Okay, so that gives you actually 1 minus probability of A, simple factorization, 1 minus probability of B, and that is nothing but your 1 minus probability of A is A complement into probability of B complement. So you have started with A complement intersection B complement, and you have proved that that is equal to probability of A complement into probability of B complement. So A complement and B complement are independent with the assumption that A and B are independent. Okay, so this is our lecture today. I hope this is interesting to you, because we are talking about mainly on independent events and mutual independent, pairwise independence, and some important observations on that. And lastly, some examples, some proof of simple problems. Okay, so let me explain more on probability in the next video, next recording session, and next class. Okay, thank you all of you.